So in 4.5, we talk about undetermined coefficients to find a particular solution for a non-homogeneous linear differential equation in the approach by operators or annihilation. In 4.4, we discussed the same method with superposition approach. So that's just one method in different versions to find a particular solution of a non-homogeneous differential equation. Today, we're going to discuss another method to find a particular solution for the non-homogeneous differential equation. It's called the variation of parameters. So we're going to discuss the general theory of variation parameters, and then we're going to discuss some examples. Let's just start from homogeneous equation first, okay? So suppose we have a linear second order non-homogeneous differential equation to solve, y double prime plus p, y prime plus q, y equals f. And suppose y1 and y2 are two linearly independent solutions of the associated homogeneous differential equation. Then the general solution of this associated homogeneous differential equation will be C1y1 plus C2y2, where C1 and C2 are arbitrary constants. In other words, the general solution of the associated homogeneous differential equation is the linear combination of two linearly independent solutions of the homogeneous equation. So this is the solution for the associated homogeneous equation, but we're trying to solve a non-linear, non-homogeneous differential equation, okay? The right-hand side, f is not 0, okay? Now, by the way, associated homogeneous differential equation means you drop the f on the right and put 0 there, okay? So let's just use the same approach or borrow this idea in finding the particular solution of the non-homogeneous equation. So in order to find a particular solution yp of the original non-homogeneous differential equation, we can write the form of yp to be u1 y1 plus u2 y2, where u1 and u2 are both functions instead of constants. Okay, because we're trying to find a particular solution to the non-homogeneous equation. So u1 and u2 cannot be both constants, because that would just give a solution to the associated homogeneous equation, not the non-homogeneous equation. So u1 and u2 have to be functions. Okay. So then we just plug in this form of yp into the non-homogeneous differential equation, and then try to solve for u1 and u2. All right. I don't know who came up with this idea, but it turned out it works pretty well. So let's just take the first derivative of yp. We have two terms. Each term is a product of two functions. So we have to use the product rule for both terms. So in the first term, we just take the derivative u1 times y1 plus u1 times derivative y1. And in the second term, we just take a derivative u2 times y2 plus u2 times derivative of y2. So that's just the first derivative of yp. And then we need to take the second derivative of this particular solution yp. So what we do, we just take the derivative of y prime, okay? So y prime has 4 terms. Each term is a product of 2 functions. Remember, u1, y1, u2, y2, they are all functions of x. And when you take the derivatives, u1 prime, y1 prime, u2 prime, y2 prime, they're all functions also. So we have to use the product rule for each term. Then we're going to get the 8 terms in y double prime, yp double prime. So we get u1 double prime y1 plus u1 prime y1 prime from the first term. And we get the u1 y1 double prime plus u1 prime y1 prime from the second term when we take the derivative of yp prime. And then we get the u2 double prime y2 plus u2 prime y2 prime from the third term of yp prime. And then we get the u2 prime y2 prime plus u2 y2 prime y2 double prime from the fourth term of yp prime. All right, so these are 8 terms that we can combine like terms. We can combine 2 terms of u1 prime, y1 prime, and 2 terms of u2 prime, y2 prime. Okay, so we end up with 6 terms in y double prime, yp double prime. Then we just plug in yp double prime and yp prime into the differential equation. On the left, it's yp double prime plus p, yp prime plus q, yp. So just plug in everything we got in previous steps. So so we got a now expression on the left hand side. So I'm not going to repeat everything. We got yp prime, yp double prime, just plug in. But then we can rearrange those terms. We're going to group all the terms with u1 prime, u1, and we're going to group all the terms with u2, and factor out u1 and u2 from those terms respectively. So the whole thing just becomes u1 times y1 double prime plus py1 prime plus qy1 plus u2 times y2 double prime plus py2 prime plus qy2 plus u1 double prime y1 plus 2u1 prime y1 prime plus u2 double prime y2 plus 2u2 prime y2 prime plus p times u1 prime y1 plus u2 prime y2. Okay. So we also factor out p from some other terms at the end. But we know y1 and y2 are solutions of the associated homogeneous differential equation. So that means y1 double prime plus p1 y prime plus q1 qy1 equals 0. And y2 double prime plus py2 prime plus qy2 equal to 0. All right. So then the left-hand side of the equation just becomes u1 double prime y1 plus 2 u1 prime y1 prime plus u2 double prime y2 plus 2u2 prime y2 prime plus p times u1 prime y1 plus u2 prime y2. Okay, still we got a bunch of terms, but it's much more simplified. All right. So that's the left-hand side of the differential equation. All right. So now we can rewrite this whole thing by the derivative of u1 prime y1 plus u2 prime y2 plus u1 prime y1 prime plus u2 prime y2 prime plus p times u1 prime y1 plus u2 prime y2. Okay. You can easily check that if you're not sure. What you do, just take the derivative of this u1 prime y1 plus u2 prime y2, and using the product rule again on each term, and then you can see, this whole thing can be written as this. All right. So this is just the left-hand side of the differential equation. The right-hand side of the equation is just f. So we have this whole thing equals f. So this is still a hard equation to solve. We got u1 and u2 to solve from this one equation. We know y1 and y2 are two linearly independent solutions of the associated homogeneous equation. So y1 and y2 are given. But we still have two functions, u1 and u2, to solve from this differential equation. So we have some freedom to choose what u1 and u2 will be. You have one equation with two variables or two functions to solve. So you have some freedom to choose of those two functions. Just like you try to solve an equation with two variables, but you only have one equation, so you can have some freedom to choose for the solution. There will be infinitely many solutions, actually. All right. So why don't we just choose u1 prime y1 plus u2 prime y2 equals 0. So the third term on the left-hand side is p times u1 prime y1 plus u2 prime y2. Why don't we just let this term vanish? And then also you can see, the first term is just derivative of that. u1 prime y1 plus u2 prime y2. So then the only thing left on the left will be just u1 prime y1 prime plus u2 prime y2 prime. So that has to be fx if we have this choice. If we take this choice. And that simplifies a lot for the equation itself. All right. So you can have some other choice, but this turns out to be the best choice because it just vanishes the third term and the first term. Okay. And then we can easily solve for u1 prime and the u2 prime from these two equations, because we know y1 and y2. Okay. You can use, elimination method to solve this system of equations. Just like solve other equations with variables, we only have u1 prime and u2 prime to solve. So you can eliminate either u1 prime or u2 prime from these two equations and solve for the other. Or you can use determinant matrices using determinant matrices to solve it. But at the end, we get the u1 prime equals negative y2 f over y1, y2 prime minus y1 prime y2. And u2 prime equals y1 f over y1, y2 prime minus y1 prime y2. Okay. So now all of the functions, y1, y2, and f, we know. Okay. Then you can just simply integrate in each equation to obtain u1 and u2. Then you just plug in back to the original expression for yp. So we solve for u1 and u2, and then y1 and y2 are given, or we can find those y1 and 2 easily from the first step. Okay. So then in this way, we found a particular solution of the non-homogeneous equation. All right. So the theory itself is complicated to derive the formulas. But at the end, you just use those formulas to find a particular solution yp. All right, you don't have to, derive all the formulas again. So that's called a variation of parameters. All right. So in here, u1 and u2 are just two parameters. Okay. They're not constants anymore. So that's variation of parameters. C1, C2 are becoming functions. So we just change those constants to functions. So that's called the variation of parameters. Any questions about this method? I know this formula is a little tedious and a little messy, but you have to be careful when you try to work on this formulation. But at the end, the result is relatively simple. Okay. So let's just try to do one example. Okay. Today. So suppose we want to solve the differential equation of y dot prime plus y equal to sec x by a variation of parameters. All right. And you can see the right hand side is sec x is a trig function, but we did not discuss this kind of functions in previous sections. In the previous sections, the right hand side is either cosine or sine functions or exponential functions or polynomials or combination or product of those functions. But there has never been a secant x or tangent x and or other things. So it turns out the undetermined coefficients method will not work. Remember, we have to have those terms or those forms of functions to use undetermined coefficients. They have to be either polynomial or exponential functions or cosine or sine functions or combination and the product of those functions. So the only thing left for us is just the variation of parameters. So why don't we just use this new method to find a particular solution of this equation? Okay. So the right hand side f is just the secant x. So again, we have to solve the associated homogeneous differential equation. We put the right hand side equal to 0. So that's just the becoming y dot prime plus y equal to 0. And again, you solve it by letting y equal to e to the mx, plug into the equation, and then do a little simplification. And then we get the auxiliary equation m squared plus 1 equal to 0. If you do that, we have done this so many times. So I'm not going to repeat the details. So you can easily solve for m from this equation, and you get the plus or minus I. If you move 1 to the right, you get the -1 m squared equal to -1. When you take the root, you get both plus or minus I. Okay, we got the complex solution, or two complex solutions. So then that will give us two linearly independent solutions. Cosine x, sine x. Remember, whenever you have imaginary part in this m, you get cosine or sine functions. So in this case, they're just cosine x, sine x. Okay, we don't have any numbers in here, so that means it's just x, and we don't have any, no number to multiply this I. So it just gives the argument x, and also we don't have any real part for this m. They are pure imaginary. So that means we only have cosine x, sine x. We don't have exponential functions. Okay. If you remember how to solve homogeneous differential equations. So these are the two linearly independent solutions for the associated homogeneous equation. We call them y1 and y2. Okay. Now we just use the variation of parameters, which is yp equals u1 times y1 plus u2 times y2, where u1 and u2 both are functions. And the formulas for u1 prime and the u2 prime, it's just that. I just copied it from the previous page. So you just plug in, y1, y2, f in each formula. All right, so let's just do that. So u1 prime equals negative y2 f over y1, y2 prime minus y1 prime, y2. Okay, so y2 is just sine x. So sine x prime, y2 prime. And y1 is just cosine x. So we got the cosine x in here, cosine prime x in here. All right. And the f is secant x. Okay, that's the right-hand side of the equation. All right. So we can, just do the sine x to get the cosine x, and the derivative of cosine x to get the negative sine x. So then what? So then we get cosine x times cosine x, which is cosine x squared minus negative sine x times sine x, which is plus sine x squared. So cosine x squared plus sine x squared is just 1. So the whole thing is just negative sine x secant x. But if you still remember the reciprocal relation in trig, secant x just 1 over cosine x. So we can rewrite the whole thing as negative sine x times 1 over cosine x, or just negative sine x over cosine x. So that's just u1 prime. And similarly, we can get u2 prime from the other formula. So that's just y1 f over y1, y2 prime minus y1 prime, y2. So again, y1 is cosine x. Y2 is sine x. Just plug in, and f is secant x. All right. Again, the denominator is cosine x times cosine x minus negative sine x times sine x as before. That's just cosine x squared plus sine x squared, which is 1. At the same time, cosine x times secant x just 1, because secant x is 1. It's just 1 over cosine x. So the whole thing is just 1 over 1, which is 1. So u2 prime is 1. So then we can easily, integrate the y1 prime to get u1 prime to get u1, and u2 prime to get u2. So u2 is just very simple. It's just x. Okay, if you integrate the 1, you get x. And you can easily integrate negative sine x over cosine x to get the natural log of absolute cosine x if you rewrite the right hand side as cosine x prime over cosine x. Remember, cosine x prime is just negative sine x. So you can write this whole thing as cosine x prime over cosine x. And then you use substitution u equals cosine x. So then you're gonna get the u prime over u, which you integrate to get the natural log of absolute u, where u is cosine x. Okay. So by the way, we don't have to worry about the arbitrary constant, C1 or C2, in each of those answers or integrals, because we just need to find one of those solutions of U1 and U2. So then plug in U1 and U2 into this YP. So we get the YP equals U1 Y1 plus U2 Y2, which is cosine X, that's Y1, U1, natural log of absolute cosine X plus U2 X times Y2 sine X. Okay. So this is just the particular solution we found for the non-homogeneous equation, and to find the general solution to the equation. So remember, YP is just a particular solution. So we need to solve for this non-homogeneous equation. We need to find a general solution of this equation. Then you just add the general solution of the associated homogeneous equation, which is C1Y1 plus C2Y2, and then add this particular solution YP. So the whole thing is just C1 cosine X plus C2 sine X plus cosine X natural log absolute cosine X plus X sine X. Okay. Remember, this is Y1, Y2, there are solutions, linear independent solutions of the associated homogeneous differential equation. So this is the answer for the final answer for the problem. Any questions?